Need to open that. Right, so everyone should have a copy, just to double check. Does everyone have a copy of the Infinite Time Horizon notes in front of them? Last chance, if you don't, I've got a set of notes to say Part 4 Infinite Time Horizon in front of them. Okay, assuming is yes. Yes. Great. Okay, great. Right. So, yeah, okay, here we are. Good. So now we're going to kind of work with problems where there's no definite end time to them, okay? That can be quite important in financial examples as well, where you want to maximize long-run quantities with decisions over shorter time periods, okay? So thus far we've considered finite time Markov decision processes, but now we want to solve Markov decision processes of the following form. Well, we want to maximize over the set of policies, where policy is exactly the same as before, but we don't have an end date. Okay, so again, a policy that I choose at time t is a function of the actions that I've chosen previously and the states that I've visited previously. Okay, we want to maximize the reward. Okay, and here the reward is the expected value, give my initial state x, and that should say x here, just x rather than x0. Okay. So given I start at x equal x0, okay, I get a reward for the state that I'm in and the action that I choose at each time, okay, and I sum up the rewards from time 0 to infinity, okay. And obviously there can be some issues with summing up. Let's say I get a reward of 1 at every time, okay. There could be some issues with this sum if I'm summing up 1 infinite many times, so it's going to get infinite. Okay, so often what people do, both in Markov decision processes and in reality, is apply some sort of interest rate. Okay, so we discount the value of the rewards in the future by some factor that goes down at each time. Okay, so when considering an infinite time model of a Markov decision process, people often apply this factor to it, okay, and is often interpreted as being sort of interest rate, okay, in a financial application, okay. Right. So now things get a little bit more complicated in some respects for when we go to infinite time. We have to distinguish between different cases where the theory is going to work, okay. So because we don't have a finite problem or a finite time problem, then we have to be a little bit more careful about what conditions we have on our model, so that things like when we solve Bellmans equation, we can make some meaningful interpretation about what that means about the optimal solution. Okay, so we're going to divide things into 3 cases. Okay, positive programming, negative programming, and bounded programming. Okay. So what are those? So maximizing positive rewards is called positive programming. Okay? And it doesn't really matter what these betas are. All right? It could be anything as long as it's positive. Okay? Minimizing losses, okay? So that's minimizing costs or minimizing losses, is called negative programming. Okay? So minimizing positive losses or maximizing negative rewards is called negative programming. Okay? Then maximizing bounded discounted rewards, so that is where The reward function in here is bounded by some constant b, okay? And there's some discount factor applied, beta, which belongs strictly in the interval 0 to 1, okay? So rewards in the future get worth less and less and less over time, okay? In that case is called bounded programming, okay? Okay, so 3 cases: positive programming with positive rewards, negative programming, which is maximizing negative rewards, or equivalently minimizing costs, positive costs. Okay, and then bounded programming, which is where the rewards are bounded and we pound some discount factor. Okay, those are sort of the 3 main cases where we can make meaningful interpretation of the Bellman equation. Okay, some people just sort of throw caution to the wind and we just solve Bellman's equation and just hope that tells us something about the optimal solution. Okay. Okay. So most of the definitions that I've given so far relate to maximizing rewards and values, and this definition here is just to mention how the kind of notational changes I'm going to be making when we talk about minimizing costs or losses. Okay. So there's nothing new in this. It's just I want us to go through the notation. That, okay. So if we're minimizing losses, okay. So far everything that we've considered has been maximizing rewards. However, often we want to minimize losses or costs. And when we do this, we're going to use the following notation. So L is going to be our optimal loss, okay, the minimal loss, okay. So before, for a maximization problem, it was either W or V, okay. This is minimization of the sets of policies. Policy has exactly the same definition as before. Rather than a capital R here, I'm going to have a capital C for cost, okay, and I'm going to be taking the expected sum of all the losses, okay. So just a little bit of notation changes there, nothing too fancy, okay. So I kind of wanted to give briefly the idea of why these cases are different in infinite time. There shouldn't seem to be any difference between minimizing negative programming and positive programming. Okay, so this is essentially why. Okay, so first, this question says, show that, let me get my part, says show that for R of t being the finite time Markov decision process over t time units, like this, show that this converges to that for a given policy and is less than or equal to the optimal reward function. Okay, and that's not too difficult a question. So essentially you can note, so the answer here is to note that R of t pi equals E sum of t equals capital T minus 1 beta t R of x of t pi of t. Well, this guy goes up to the sum from t equals 0 to infinity, okay, beta t R of x of t pi of t. And why is that? Well, it's just monotone convergence theorem, or in the case of bounded programming, bounded convergence theorem. Okay, so that holds here is monotone convergence theorem or bounded convergence theorem. BBCT means bounded convergence theorem. Okay. All right. And that gives me my reward function for executing that policy from state X. And obviously it's trivially true that this is less than the maximal one, the optimal one. Okay? So that's kind of trivial. Okay? Then, exercise 4, again, nothing too hard. show that the optimal cost function up until time t, which is this finite sum, converges up to c of x of t. Okay, again, that is just monotone convergence theorem. Okay, and of course, the cost for any specific policy is bigger, than the minimal cost. Okay, so that's fine. Right. So what's the point in saying that? It's all kind of not very difficult. Note that the reward function here, essentially, each time that I add to the reward function increases the reward, and each improvement that I make on the policy increases the reward. Okay, so both increasing time and changing the policy in a good way moves you towards the optimal policy. Okay, so everything sort of harmoniously points in the right direction. Okay, whereas if we're looking at costs rather than rewards, okay, notice that as I increase time, okay, I sort of overshoot the optimal loss function. So I could start with a finite time problem that kind of goes up and up and up and up, increases past the loss function, and after I've taken the infinite sum, I have to decrease it back down to the optimal loss. Okay? So sort of like one, everything moves in the right direction towards the optimal reward. The other one, you sort of overshoot it and have to bring it back down again. Okay? So for sort of that reason, at a high level, that's why the two cases have to be treated differently. Okay? Of course, we'll see that in a bit more detail when we go through the proofs of some of these. I probably will just do the proof for positive programming. I might do some exercises or give some notes on the negative programming case. Okay, so I want to kind of prove why solving Bellmans equation for positive programming is going to give the right outcome, going to give you an optimal solution. Okay, so that's the next part. So Bellmans equation for positive programming. Okay. We now discuss Bellmans equation in the infinite time horizon setting. Okay. We previously looked at Markov decision processes inductively with Bellmans equation. So we started with a solution at time capital T, and we worked backwards inductively to solve it. In infinite time, we cannot directly apply induction. Okay. However, we see that Bellmans equation still holds, and we can use this to solve a Markov decision process in infinite time. Okay? And this theorem sort of states that this is okay. This is an okay thing to do. All right? So it says, for the case of a positive program or a discounted program, given the limit Rx of t, which I interpret as the limit that I described before, you take the finite type problem and let t goes to infinity. Given these limits are well defined for each policy, the optimal policy satisfies this expression, which again is Bellmans equation. Okay, that the optimal value function, you take the maximization over the actions that you can take at that point in time. Okay, then you get the reward, the instantaneous reward for taking that action from that state x, and then you go to the next state, x hat, and you do the optimal thing from there onwards. Okay. Now, obviously, that next state is random, so if we're maximizing expected rewards, we need to take an expectation here. And because some interest has been applied over that time, because somehow the money in 1 unit of time is worth a bit less than the money now, we have to apply the interest rate factor here as well. Okay? But notice all of the kind of logic that we used before applies in the same way. You maximize your instantaneous reward plus your future reward, expected discounted future reward in this case. There's discount because there's a discount factor, okay, but it's still the same idea that we're looking at the expected discounted future reward, okay? Okay, so that's one thing. So if we have the optimal policy has to satisfy this equation here, all right? Oops, sorry. So this equation is satisfied by the optimal policy, okay? Well, let's now consider the situation. If we just find a function now, let's just say I find some function r which satisfies the same equation. Okay? Does that mean it's the optimal policy? And the answer basically is yes. Okay? So now, if we find a function r of x, and we find the function pi, the policy, that maximizes the argument in each of these maximizations, then pi is an optimal policy, and r, the reward function, is the reward function from that policy, and it's equal to the optimal value function. Okay? So basically, if I can solve Bellmans equation, I've solved the Markov decision process in the infinite time case. Okay? So we can't do backwards induction anymore on Bellmans equation, but if I can solve Bellmans equation, then I've got an optimal policy for that infinite time problem. Okay? Are there any questions about that result? Okay. So this is why I could have spent the whole I could have spent the whole lecture series talking about induction on Bellmans equation or something like this, or the finite time problems. But really, a lot of the algorithms and things that people consider are the infinite time situation, and this says that really we don't want to care about induction. We just want to focus on these sorts of relationships, these Bellman equations. Okay? Okay? Right. So let's now prove this. So we're gonna break down the proof of the theorem into quite a few steps. Okay? So basically between here and the start of a discussion on negative programming, which I might not prove for you, we're going to prove this result. Okay, so there's quite a few steps to it, but they're all individually okay steps. Okay.
What does the ARG max mean?
Okay, yeah, good question. So that means the maximizing argument. Let me go to the last page. I'll just make some notes on this page. Oh, too many notes. So that means, so if I've got a maximization problem, I can say the maximization over some set of some function f of a, yeah? And that means the value that f of a takes when it's at its maximum, okay? When I write argmax, I mean the argument that maximizes this function, okay? So if I say that this value is f star, the biggest value, and I take an a belonging to this argmax, then f of a, let's say a star, f of a star is a number, an argument that I can put in that equals f star, okay? Does that make sense? So it's a value that maximizes the function, okay? It's not the value of the maximal function, but it's an argument that I can put into the function that maximizes it, okay? Obviously, not all problems have a maximizing argument, but for the sake of this course, we might as well assume that they do, okay? All right. Okay. So it's a good question to ask because we're going to be writing maxes and argmaxes quite a bit, so it's a good one. Okay. Right. So let's show this theorem. So it's going to kind of come in two parts. We're going to show this part first. All right. And then, depending on the amount of time we have, we'll work towards the second part, the moreover bit. Okay. So the first part is going to consist of showing that the optimal policy, the optimal value function v satisfies this expression. Okay. And then we'll work towards saying if I can find something that solves the Bellman equation, then it's also optimal. Okay. So first part. So show that r of x of pi is equal to x of pi 0 plus beta r of x hat pi hat, where pi hat here is the policy that is taken by pi after taking its first action from state x. Okay? And x hat here is the state reached by the policy after taking that action x in policy pi 0. Okay? So basically, this is the first reward that you receive. Given the reward and action that you chose, that's the state you arrive in, and that's the policy that you follow thereafter. Okay? And, well, it's kind of, I'm not even sure if it really needs to be proven this, but one way to, one way to show this, we could think of this, that if I did the finite time problem, okay, and I looked at the rewards of the finite time problem from time t, it will be equal to the reward of little pi of 0 plus beta, the expected reward from time t plus 1, of the function, the value of the state of the next time, okay, where x hat means the state that I arrive at after being in state x and taking action a0, and then pi hat is the policy that I follow, given the first two decisions that I've made. Okay, I mean the first decision that I've made in terms of actions. Okay, and then I just apply monotone convergence theorem to both sides. Okay. So in particular, if I apply monotone convergence to this guy, it's going to go to Rx of pi. And if I apply monotone convergence to this guy, it's going to also go to Rx hat pi hat. Okay? And then I'm just going to arrive at the expression I wanted. Okay? Okay. Next bit. Okay. We're going to show sort of half of the thing that we're after now. So we do the easy half. In particular, we're going to show that this expression holds, but with an inequality here. Okay? So why is that? Well, I've got this equality here, and I could replace the reward in here with the optimal reward. Okay? If I put in the optimal reward, v, would this make this bigger or smaller? Yeah, bigger. Yeah, that's just going to make the expression bigger. Okay? So let's do that. Okay. Now, if I maximize this over the action that I take first, this side of the expression, that's also going to make it bigger. Okay, so I've taken one action pi 0 here. Okay, but if I maximize over all the actions, that's only going to make things bigger again. Okay. Okay. I've got an expression that says no matter what I put in here as a policy, it's always going to be less than this. Does everyone agree with that? So notice this expression doesn't depend on the policy pi that I've chosen. So it's like it's an upper bound for all reward functions and all policies. Okay? So now if I maximize this, expression over pi, okay, I'm going to arrive at v. So if I maximize now the left-hand side, this is going to give that v of x is less than or equal to the max over a r of x of a beta e of x of a v x hat. Okay? That's it. Okay? So now 1/4 of the way through the proof. So now we've got to prove the inequality in the other direction. So we've got this with this less than or equal to that. And now we need to show that v of x is bigger than this. All right? So in the following exercise, or exercises, where we continue to give the proof, we're going to let pi of epsilon be the policy that chooses action A, and then from then on, in the next state, x hat, chooses a policy pi epsilon, which is within a factor, oh, and that should have, excuse my typos, this should be x hat in here, so there's a typo there. Okay. So it chooses a policy that's within epsilon of the optimum. Okay? Since this is the optimal policy, it has to be a policy that's within epsilon of the optimal policy. Okay? So now we're going to show that this holds. That the optimal policy V is less than the instantaneous reward plus beta times the reward from the next step minus some epsilon. Okay? So notice V of x is less than or equal to something to do with the actions. Okay? So just going back to this expression here, saying V of x here is less than or equal to something like something inside these brackets. Okay? So we're now trying to get the other direction with the inequality the other way around here. We've got something very similar to that here. Okay? Okay? Well, so let's prove that. So well, v of x is certainly less than or equal to the reward from x that I get from this policy I've just defined, r of pi. R x of pi epsilon, sorry. Okay, from this policy here. Okay? Then let's write out the reward that I get from this. So I get a reward x of a at time 0. I'm in state x and I take action A. Okay. Then, from there on out, I'm going to get the reward from this function here. Okay. And then I've assumed that the policy that I take after the first action A is going to be within epsilon of the optimal one. So then, substituting my assumption in, I'm going to have this is less than epsilon beta, okay, which is what we wanted. Okay, we're kind of feeling like we've got something close to the optimal solution now. So now we can actually show that the optimal value function now satisfies Bellmans equation. We've got an inequality in this direction, so we just need to complete this and say the inequality goes the other way. Okay? So let's do that. So from exercise number 7, we have that v of x is less than, and now note I could maximize this expression over a. Okay. Now notice that this expression here doesn't depend on epsilon. Okay, this doesn't depend on epsilon, this doesn't depend on epsilon. All the information about epsilon I used to get till this point I haven't used. Okay? So essentially I can just let epsilon be any number that I like. Okay, and this inequality is going to keep holding. Okay? So I can let epsilon go to 0. All right? And also, we have from exercise, let me get the number, from exercise 6, we have the inequality in the other direction. Okay? So we're done with that part. So we basically have the inequality in both directions, and so the optimal policy must satisfy this Bellman equation. Okay? Okay. So now we're going to work a little bit towards the second part of the proof. Okay. So now, just to recap where we are, we have now shown that this holds. That if you've got the optimal value function for a Markov for a positive program, satisfies Bellmans equation. Okay. So now we want to say, well, that's great, but now we need to. If we actually solve Bellmans equation, is that going to tell us something about the optimal rewards? Okay, so now this is next part. If we find a function r of x such that this equality holds, then have we solved the problem? Okay. Okay, well, let's start with the following. If we find a reward function r of x and a function pi of x such that this equality is satisfied and pi of x belongs to the maximizing argument of all of these, then the function r of x is equal to the optimal reward function. Okay? So let's answer that. And this really isn't an obvious question. Okay? Just because I've solved this with all these equalities doesn't necessarily mean it's the optimal reward function. And this is actually kind of why we spent quite a bit of time working on the potential theory arguments for Markov chains, because we're going to use that now. Okay, so when we discussed about potential theory for Markov chains, then that was in part so we could use these kind of arguments. Okay, so notice by assumption that r of x is equal to rx of pi of x, okay, plus beta e to the x pi of x are x hat. Okay? Okay, and now let's just track back. I'm just going to go back in the notes to our discussion on Markov chains. Okay, so we proved a result that said that if I solve this equation, okay, then R is a unique bounded solution to an equation that looks like this. The long-run reward is equal to the instantaneous reward times beta times the expected value of the next state. Okay? So that was exercise 11 on our Markov chains notes. Okay? So jumping back to here, this is exactly the same thing. All right? So from exercise 11 in the Markov chains notes, it must be that Rx of pi is equal to R, because the reward function that sums the rewards must satisfy this equation, and anything that satisfies this equation is the unique bounded solution to that equation. Okay, so any solution that I can find that's bounded, okay, and any pi that I can find that satisfies this is going to give the reward function. Okay, so that's kind of why we did that potential theory type argument for the Markov chain stuff. Okay, so you don't typically do a lot of potential theory when you do a Markov chains course for the first time, but we need it for this. Okay, so that's why we covered it. All right, so we're kind of part of the way through. I'll recap from next time, but let's just quickly remember where we are with it. So we nearly proved this theorem. We've got this with equality here. We said if we can find a function R of policy pi, then this holds, that R of x is equal to R of pi. And now the last thing, the very last thing we need to show is that it's equal to v. Okay, so just that little red line is what we're left with now to prove. Okay? All right, we'll do that next week. Okay? Thanks for coming. Cheers.